So, hi everyone, my name is Jacob, and yeah, so I'm going to talk to you about daily energy expenditure and hens with keel fractures. So as humans, we're always interested in performance. The performance of our cars, the performance of our computers, and the performance of our athletes. But unfortunately, our athletes, they don't run on gas or electricity. They use the metabolic process to achieve sports at a high level. The energy that they consume is all goes through the metabolic process. When these athletes face injuries, like a bone fracture, they can take up to 24 weeks to return to performing. They spend much of this time resting, with medical teams and rehabilitation teams at their side, working to get them back to tip-top shape. And though these athletes demonstrate these amazing feats, there is an unsung hero that's been performing at the top of its game. The laying hen has been bred to produce one egg each day, a true masterclass of energetics. When these hens experience an injury, like a keel bone fracture, they can't take time off. They continue to lay the egg day in and day out, without that extensive medical team at their side. Now our athletes, they retire young. They're 30, they're millionaires. But our lay hens, they keep on performing even as they age. These so-called end-of-lay hens are what I want to talk to you about today. In this study, we look to investigate how the occurrence of keel bone fractures in the life history of a hen influence their daily energy expenditure. It's crucial for us to develop an understanding on how these high-performing birds modulate their metabolism to deal with injuries in the short and long term. So, just to get started, let's talk about keel bone fractures. A keel bone fracture is a fracture of the keel, or the sternum, of the bird, and it occurs 95% of the time to the distal part of the keel bone. These fractures are prevalent in all lay hens, but age, strain, and housing system do affect the severity. An individual hen can have up to 5 keel bone fractures, and they occur in the largest proportion at peak lay. Healing one of these fractures can take 4 to 6 weeks, with the formation of a hard callus indicating the conclusion of healing. Though this can vary depending on the severity and location of the fracture, however, it's well understood that healing a fracture of any kind is highly energy intensive. In end-of-lay hens who experience keel bone fractures, there's been no evidence of detrimental welfare effects. Hens present with normal behaviors, activity levels, fearfulness, mobility, and even lame biomechanics. This leads us to wonder if there are any physiological differences in hens with and without keel bone fractures. In hens still affected by a keel bone fracture, we would expect them to have a larger daily energy expenditure as they mount an immune response to heal said fracture. So measuring daily energy expenditure in end-of-lay hens with keel bone fracture could give us insight into the potential associated effects. This would need to be done in a hen performing a natural behavior. So we use a method called doubly labeled water. Doubly labeled water is a method of measuring the usage of hydrogen and oxygen in an animal, following these elements of the animal system. But you can't just follow any hydrogen and oxygen. You have to label it somehow. So we use isotopes of hydrogen and oxygen called deuterium and oxygen-18. Both these isotopes are eliminated in body water in the form of sweat, evaporation, and urine. However, only oxygen-18 is released in carbon dioxide. So it's the divergence of these two elimination rates that allows us to determine the CO2 production of an animal. This method is widely used in humans. It's considered the gold standard, but it comes with some downsides. It's incredibly technical, mathematical, and expensive. So the aim of this project was to determine the energy expenditure of hens aged 92 weeks of age and investigate the impacts of keel bone fractures in end-of-lay hens using doubly labeled water. We hypothesized that keel bone fractures would not influence the daily energy expenditure in end-of-lay hens, just as keel bone fractures don't impact behavior and the effective state. So to accomplish our project's goals, we used 120 brown and white feathered hens, bred in an apiary system until they were 17 weeks of age. We moved them into 12 multi-tick systems and housed them here until they reached 92 weeks of age. In that time, they developed keel bone fractures. All 120 hens were radiographed, and upon analyzing these radiographs, we noticed that brown feathered hens showed a larger proportion of clearly defined calluses forming at the fracture site and had more fractures. So for this reason, we focused on brown fractured hens. A random sample of 8 hens with keel bone fractures and 8 hens without fractures were selected, and upon further analysis, we found that all of the hens we selected with keel bone fractures had severe fractures. So just to briefly go over our methods, you can see first we radiograph, we x-ray, we weigh, and we we eject the isotope. Hens are then restricted for 1 hour for the isotope to equilibrate with the body, and then we collect some blood. This is our baseline collection. Hens are then allowed to freely roam for 48 hours after a second, followed by second blood collection, and then blood was sent to George Fox University for analysis. So we weighed the hens, and this is important to calculate the individual dosage per hen. We ended up dosing 1.682 milliliters on average, and we then need to collect some blood. This blood collection is important because oxygen 18 and deuterium exist naturally in tap water. You've all got it in your body, so we need to see how much is in the hens naturally. This blood collection is collected in a capillary tube, which then needs to be flame sealed because we need to preserve all this blood and not allow for any evaporation. Prior to the injection, using the dosage, the individual dosage calculated, we use a precision syringe, and we need to be really precise about how much of these isotopes we're giving each hen. Each hen then receives an injection intramuscularly to the pectoralis muscle. We want to make sure that we're accounting for the fact that intramuscular injections aren't comfortable, so we're rotating back and forth between left and right pectoralis to account for any associated behaviors. Hens are then kept in a dog crate for 1 hour, and this 1 hour is really important as the injectate needs to completely balance and equilibrate with the normal body water. And then we do a second blood collection. Done in the exact same order hens receive the injection, again collected in a flame-sealed capillary tube, and then sent off. This the second blood collection is actually our baseline. After this injection, hens are returned to their home pens for 48 hours. And this is where doubly labeled water is unique to experiments like respiratory chambers. It allows for the hen to freely roam and do their normal behaviors. After that 48 hours, hens were collected, and again, blood was collected in the exact same order that hens received their injection in flame-sealed capillary tubes, and this is our final. So now we know the divergence of these two isotopes. Blood was then shipped to Dr. Donald Powers at George Fox University, where it can be centrifuged and microdistilled. Microdistillation of these samples allows for separation between blood components and body water. And then body water can go through isotopic ratio mass spectroscopy, so we can analyze the concentrations of the isotopes in the blood. So now what we have calculated from the divergence, we know the carbon dioxide production, but we want to know daily energy expenditure. And this can actually be done quite simply by using what is called a calorific equivalent, so we know what 1 milliliter of CO2 production is in energy sense. So we used 20.1 liters of CO2 produced was 1 kilojoule of energy. Getting into some results now, we found that our results have large variations within them. We see daily energy expenditure ranging from 788 to 1,350 kilojoules per day, and daily energy expenditure by weight ranging from 355 to 730 kilojoules per kilogram per day. But this sort of variation isn't unheard of in metabolic research. Daily energy expenditure is an overarching measurement that contains our rest metabolic rate, our diet thermogenesis, and our activity thermogenesis. Our resting metabolic rate is what consumes most of our energy. 60 to 75% of our energy goes towards this. But this isn't where our variation comes from. Most of the variation comes from what is called non-exercise activity. So this is based on age, genetics, body composition, and it could really be the difference between someone who chooses to sit at a desk versus stand at a desk. To investigate the effects of keel fractures on energy expenditure, we use a linear mixed model in SAS with fracture stats as a fixed effect. We found no difference in the daily energy expenditure or daily energy expenditure by mass in hens with and without keel fractures. When comparing our results to existing literature, we see that the main theme is that our hens in the study at 92 weeks of age displayed a lower energy expenditure and daily energy expenditure by mass, and this is likely due to a combination of several factors. As shown by Renee Grant et al., brown feathers hens spend more of their time on the ground, and we know that this behavior can increase with age. Additionally, egg-producing hens at end of lay will be laying closer to 70% efficiency versus peak lay where they're laying at 100% efficiency. So this discrepancy in egg production was likely seen in our lowered energy expenditures. So to talk about some of our key takeaways, this work is the first work where we're seeing where we're quantifying the daily energy expenditure of free roaming hens in end of lay. We also did not find any differences of the average daily energy expenditure of hens with and without keelbone fractures. Without a difference in this daily energy expenditure, we assume that fractures are healed by the time they reach 92 weeks of age, as we're not seeing the large energetic cost associated with mounting an immune response to heal the fracture. Additionally, when looking at existing literature that investigated the impact of keelbone fractures at end of lay, we see that there's no evidence of changes in major welfare indicators like behavior and affective states. This knowledge, in conjunction with our daily energy expenditure measures, leads us to conclude that there is likely no indication that keelbone fractures have a detrimental welfare effect in end of lay hens. And further research is needed at peak lay and hens with fresh fractures. I'd like to thank you for your attention and ask if there's any questions.
You chose to look at that specifically to measure daily energy expenditure, and if there were any other methods to measure this that you considered?
Yeah, so that's a good question. We use oxygen and hydrogen because through the metabolic process, water is used extensively. Hydrogen and oxygen can be tracked, both leaving as body water and only oxygen leaving as carbon dioxide, which allows us to estimate the carbon dioxide rate. So this is a widely used method. Very rarely used in agriculture because it's so expensive. You're not going to see it really in larger animals. You're not going to see it in pigs or cows because you wouldn't have such a small sample size with how expensive the isotopes are. And that's also why we have a smaller sample size of 16 hens. There are other methods to do this. All of them are either rely a lot on estimates or are quite invasive. So one method is to surgically implant a heart monitor, and with estimates of CO2 production that are associated and correlated with heart rate, you can have, so heart rate's this, CO2 production is likely this throughout a day. Or a real classic technique is to have a full energy budget, tracking every single behavior down to the second, and having estimates of carbon dioxide or energy associated with each of these behaviors. Yeah. Thank you for your question. Yeah.
Jacob, great talk. I have two questions. One has to do with the sensitivity of the method. And so, are you able, using stable isotopes, to show that you can change your expenditure rate by virtue of exercising the chickens, for example? Can you show that you can perturb the difference in basic metabolic rate?
Yeah, so that's a great question. Exercising, so this has to be a long-term research, right? So you have to do it in 48 hours, and really the only way to do kind of what you're asking would be to restrict them, because the water has to equilibrate, and if we do it too close to the time point, the 48 hours is based on guidelines, based on the metabolic rates that we know chickens have based on their weights, their body composition, right? So that 48 hours is kind of predetermined. So we would have to restrict them for a long period of time, exercise them, restrict them again, because they're individuals, they're going to go around. But what we have done is I just finished a respirometry experiment where we exercised hens immediately followed by doing respirometry, open flow mass respirometry. And with those results, preliminarily, we're actually still seeing that there is no effect of keelbone fracture on end-of-lay hens performing exercises.
Follow-up question has to do with hen-to-hen variability. We know in humans that the basic metabolic rate varies from one individual to another. I suspect the same is true in chickens as well.
Yeah.
So how would you know that you have a difference in metabolic rate from within one hen, whether she's had a keelbone break or not? Given that you don't know what her basic metabolic rate is.
You like what her basal resting metabolic rate is. Yeah, so that is one of the faults of daily energy expenditure is that it's this overarching thing. So if a hen is more active, and she has a higher energy expenditure, we can say, okay, that's activity. But if they're both resting there and they're neutral, how that energy is allocated to its healing, or if it's because she had ate a whole bunch before she rested and now she's digesting, there's no way to account for that. And just to plug respirometry again, that's a specific, it's a time point, time-stamped measure, which is unique, but this daily energy expenditure in its own way is unique because it allows for that free roaming. Even with the accompanying variance, it's still an important measure.
Great answers. You don't need to have your next committee meeting.
Yeah, no, the students are covered. Discount, right? Yeah, Paula, go ahead.
I just have one question. How long ago did the chickens have the fracture? I'm just wondering if the fracture was so long ago, say, I had a fracture 2 years ago.
Yeah.
I have a fracture right now. But if you asked me 3 years ago, I was like, I'm not gonna do anything,
Yeah.
right? So I wonder if they changed their energy expenditure closer to when they had the fracture compared to,
Yeah.
I tell you,
And that's a great question. So that is kind of our conclusion is that at end of play, wherever that fracture occurred, it's gone. It's a moot point. So seeing a fracture, catching a fracture at the fracture time, like I said, it's a 4 to 6 week period approximately for fully healing. Fractures are also super multifactorial. They present with edema immediately, and it's really catching that fracture, time stamping that fracture to say, okay, it happened on this day at this time, and then going backwards from that's really difficult. You need a team of radiologists, and you need to be checking those hens daily. So it would be fairly difficult, but having this knowledge of how fresh fractures impact daily energy consumption would be wildly important.
Are there any questions on Zoom? There is one question on what methods can be used to measure animal energy expenditure and why you chose the one that you did.
Yeah, so there's a couple methods. I kind of touched on a few already. So one, implanting a heart rate monitor and associating that with carbon dioxide production. One would be documenting very specifically the energy budget for a day. And then those are free roaming environments. And doubly labeled water is a more accurate measure of allowing free roaming. And then if you're going to talk more about restricted environments, there are respiratory chamber experiments, which are often done in broiler hens and laying hens. And there are also, I've done a open flow mask respirometry experiment. So that's kind of making the chamber the size of a mask and putting that on the hen's face.
Awesome.
So it's been shown that fresh fractures actually do change the type of locomotion that laying hens perform. And how do you know that the birds with and without the fractures don't have the same energy expenditure because the ones without are moving and they're spending energy that way, and the other ones are sitting around and feeling like if you didn't look at the behavior?
Yep. So that's a great point. And that is the fault of daily energy expenditure without behavioral monitors. If we go through with recordings and we're watching and associating activity budgets to the daily energy expenditure, we could have that answer. What we didn't do in the present study. So how that energy is allocated could be completely different. It is kind of a telltale sign that there is no difference in energy input or output. They're level. So the fact that energy is allocated differently while staying level could kind of indicate that maybe the allocation is pretty similar. Because if they're allocating towards healing, they still have to eat, so they're adding on top of the diet thermogenesis to heal. So you could expect an increase, but completely they could be neutral with different percentage of energy going to areas.
Yeah, Joe.
It seems like the challenge is that you really want a baseline lean alarm and then you want fresh fractures. If it was a different type of lab, you would be experimentally breaking chickens' keels. No one wants to do that. So I'm wondering, is there a way to screen young birds and then put them into the situation where they're going to break their keels naturally? So they're in a brand new alien aviary.
Yeah.
And exploit that kind of natural experiment.
And in a way that is what we did. We reared them in an aviary system. We brought them into a multi-tiered system. But like I said, it would take a team of radiologists that can, because that initial fracture presents with edema. Otherwise, you need to be able to read an X-ray really, really well. We have a portable X-ray machine at our hotel, and it's nothing like I'm sure what OBC has here, where we're not seeing that crisp X-ray. So, but so that those are the associated issues with that. 100% it can be done. It would be so intensive. It'd be x-rays every other day. It would be a lot, right? That 4 to 6 week period is quick. They are birds of prey, right? They don't want to sit around hurt. They want to get back to health.
So if anyone in OBC wants to loan Jacob and volunteer for the x-rays, give him a call. We have time for one more question. So yes.
You're just talking about how chickens are a prey species. I was wondering if you came across any literature looking at biochemical measures of stress, like cortisol. Just I know, like in our domestic species that we treat in practice, especially our prey species, they conceal pain really well. So have you come across anything in terms of biochemical markers of stress?
I have not, no, but your comment that they could be, holding back these pain responses is completely true. They could be behaving as normal, showing everything as normal because they have to. If they're the last one in the group, they're taken out, right? So that could be completely another reason that I'm not seeing this difference. Because a hen with keel and fracture doesn't have the ability to take a break, to take a day off, right?
Awesome. Okay, we'll leave it at that, and thank Jacob.